Hello, everyone, and welcome to my talk on a phase transition in large network games. My name is Abhishek Shende, and this work is in collaboration with Dipanshu Vasal and Sriram Vishwanath. I'm from University of Texas at Austin. So game theory is a powerful tool to model strategic interactions among competing agents. Since the introduction of Nash equilibrium, there has been extensive work in using game theoretical models to understand or predict real-world scenarios using strategic agents. So some of the big examples are, for example, in Acemoglu and Robinson's 2001's work, they developed a theory of political transitions in a country by modeling it as a repeated game between the elites and the poor. They show that under certain conditions, a society will transition between an authoritarian state versus democracy. And this has been observed in Argentina. Um, in Akerlof's 1967 work, Market of Lemons, where he posed a market of cars as an incomplete information game and showed that such a market could lead to having only bad cars in the market. And this is a phenomena that is observed in the real world. So, so we see many such scenarios in real world where people are interacting on a network and where each agent is affected only by the actions of their neighbors. In technology adoption, we see that when a user has to make a decision to adopt one of the technology, so for example, like in dating app, the more number of people who use a particular app, the bigger the dating pool is, and then thus more people using that app makes that app better for a particular individual. This is an example of a game with strategic complements. This is also seen in the Apple versus Android. If your friends are using Apple products more, then you would tend to get an Apple product rather than an Android. In traffic congestion example, we see something opposite. So suppose a person has to make a decision if they want to use a road on a network. And the less people there are on a road, then it is more advantageous for that person. So this is an example of a network game with strategic substitutes. We see in opinion dynamics that the choices of your friends, colleagues, or peers within your network can inform political opinion or swing who you would decide to vote for. So such examples and from the real world are studied as part of network games that involve strategic decision making and then networks of relationships. This has been surveyed extensively by Matt Jackson and Ballister in their papers. So then we ask the question, how do such network effects play a role in various phenomena observed in our society? For example, we observe something called tipping points, where a transition is triggered by some critical points. For example, during the Christmas season, it is a tipping point for increase in flu transmission rates due to crowded Christmas shopping, and cold weather. We see effects in social media, where social media influencers with a loyal and huge follower base can sway the society's opinions. We have now observed Black Lives Matter movement, which has now become a worldwide movement, but can be traced back to a few specific events in the US. During the 2016 United States elections, we saw opinion polarization where political opinions of people were affected by certain events. So is there a mathematical way to understand and predict such macro phenomena at the society level using strategic interaction of people at the micro level? We take our motivation from statistical physics. So in statistical physics, physicists have studied interaction of molecules at micro level to predict phenomena such as phase transition at macro level. So the phase transition between water and steam is an example where at a critical temperature, the density changes substantially. Such phase transitions are studied using Ising models on random graphs. And for our games on large networks, we also use random matrices as well. So looking at the survey of network literature of network games, the focus has been on understanding the effect of properties of network on Nash equilibrium. So the results in Asu's paper and Paris' paper and Ballister's paper, we see that the properties of Nash equilibria relate to the spectral radius or the eigenvalues and eigenvectors of the adjacency matrix of the network. One of the most commonly studied examples in network games is using a linear quadratic game where the best response and the utility function is a linear function, linear quadratic function. From the random matrix literature, we have seen that the work of authors in Bike, where they show that the extreme eigenvalues undergo a BBP phase transition, which changes with the strength of deformation of this random matrix. One of the biggest works by Benyak Georges and Nara Kutiti in this space is that the phase transition of eigenvectors in large random matrices can undergoes over a critical point for additive and multiplicative perturbations of Wigner and Vissard matrices, respectively. So we believe that our work is one of the first that brings this phase transition seen in statistical physics and applies it to the real world networks through random matrix and using game theory. We think that this work can lead to some systematic study of phase transitions in large games. We now set up our game and define a few network game related components. Network game with n players, where the interaction is given by the adjacency matrix G, and each player I chooses a strategy to maximize their utility function. This is a linear quadratic utility function, which is dependent on their own strategy as well as their neighbor's strategy. The Nash equilibrium is defined as the strategies which maximizes their utility over all the other strategies. For LQ game, this Nash equilibrium can be derived using first order necessary conditions to maximize this utility function, which has been derived and as shown here. We make a few assumptions over this LQ game so that we see that the Nash equilibrium X star can be interpreted as the eigenvector of the adjacency matrix G, which corresponds to the maximum eigenvalue lambda max. This helps us to make a connection between eigenvector, eigenvalue, and the Nash equilibrium and connect it to the random matrix theories. So let's look at an additive perturbation in an LQ game. So we see that X is a Gaussian Wigner matrix, and it is known and shown that the spectral measure of X, the eigenvalues, converges to the well-known semicircle distribution with the density as shown here. And then the extreme eigenvalues, the maximum and minimum, converge to this endpoint of the support, which is 2 sigma. Our perturbation matrix P is a symmetric matrix with rank R, and its eigenvalues are distributed as shown here. So from the random matrix theory and random matrix paper by Banyak Georges, we have a phase transition theorem where as n tends to infinity, that is for large matrices, where we have an additive perturbation where x tilde is equal to x plus p, the maximum eigenvalue undergoes a change where where the theta1, which is the strength of the perturbation, is above a critical point sigma, we have our maximum eigenvalue changes, while below that, the maximum eigenvalue stays the same. We simplify this a bit to use perturbations with rank 1, so that we have the perturbation matrix as theta u transpose, and we see this phase transition for the eigenvector as well, where we have two different states above and below this critical point of sigma for this eigenvector. We visualize this phase transition here. We see that the histogram of the eigenvectors, eigenvalues on the left side is within the semicircular distribution. So for the Wigner matrix, we have the eigenvalues within this red curve. On the right side, on application of an additive perturbation, we see that the extreme eigenvalue moves out of the semicircular distribution, and this is the phase transition phenomena that is observed. So how is this? How can this be applied in an LQ game? So we can see that the matrix X, and the matrix can be thought of as the adjacency matrix of a large network between modeling the interactions between different participants. We see that the perturbation matrix leads to deviations in the impacting the interactions between different players. And as we have shown before, like the Nash equilibria of this game is the eigenvector corresponding to the maximum eigenvalue. Thus, due to additive perturbation, we can observe that the Nash equilibrium is dependent on the parameter theta of the perturbation. So below this threshold value, the Nash equilibrium does not change and does not depend on the strength, but above this threshold value, the Nash equilibrium changes due to this phase transition. We try to visualize this using a numerical example for a Wigner matrix with n equal to 2000. We plot the theoretical curve as shown from the theoretical value from the phase transition theorem, and then calculate the Nash equilibrium numerically, which is just the leading eigenvector, and for two different critical values. Here, as we can see that below and above this critical value, the Nash equilibrium shifts and starts displaying this phase transition. Here, there's a bit of difference between numerical and theoretical, since these results are valid for the range of n tending to infinity. Another type of perturbation that we'll look at is the multiplicative perturbation. So for a Wishart matrix, we have the eigenvectors, eigenvalues correspond to the Marchenko-Pastor distribution with the density as shown here. And again, very similarly, the extreme eigenvalues corresponds to the endpoints of this support. Taking the similar perturbation matrix, our multiplicative perturbation is defined as x tilde is equal to x times I plus p. And so we see the phase transition where if the strength of the perturbation is above a critical value, again, we have a difference in the maximum eigenvalue. We simplify this to use a specific perturbation type with just a single rank 1 matrix, and we see that the eigenvectors also display this phase transition. So in LQ game, again, if we consider this X as the Wishart matrix to be the to represent the network of people, and then the edges, and then the perturbation, which changes some of the interactions within this network. We could think of the Nash equilibria, which is the eigenvector of the maximum eigenvalue, is dependent on the strength of the perturbation, and below this critical strength, the Nash equilibrium remains unaffected, but above this critical strength, the Nash equilibrium can be modified and can be changed. We again visualize this using a numerical example with two different critical points. The value of the norm of u tilde and u is a theoretical curve as defined from the theorem, and then the numerical value is computationally calculating the Nash equilibrium for this random matrix. We observe a similar phase transition as seen in the additive perturbation. The two curves, the Nash equilibria shifts significantly as soon as it crosses or is close to the critical point. These two curves have been show this phase transition phenomena. So for our discussion, we try to conclude using our displayed results. The Nash equilibria for this specific linear quadratic game, you can see that it can be affected through additive and multiplicative perturbation. When the perturbation strength is strong enough, the primary eigenvalue goes beyond the random spectrum, and this affects the Nash equilibrium. The finite rank perturbation of an adjacency matrix of a large network can be interpreted in multiple ways. The additive perturbation can be defined such that the specific nodes of a network have higher influence through their edges on the neighbors and consequently the entire network. The multiplicative perturbation is a bit difficult to visualize, but there can be some work done there to analyze what that would mean. So using an analysis, we see that we can apply sufficient external modifications to a network targeting an influential set of individuals to trigger a large cascade of value spread. We hope that this opens up a bigger picture of combining random matrix theory and network games, even outside of LQ games, and apply it to some different network game models. These are a few references that we have used for our work. Thank you.